Hey guys, what's up? Eddie Aho here with kissanalog.com. Alright, so I did a first power up on this Class A amplifier, this Aleph 5, 60 watt Class A. Did the first power up, wanted to make sure that I had installed all the parts right and everything was working, and it looked like it was, so that's awesome. It's been very careful and all that good stuff, powering cycling a few times. But at one point we looked at the FFT and we saw some spikes. They look like too many spikes, too high value maybe. So today what I want to do is delve into that. I've had some really good comments, suggestions, ideas on the last video. Thanks guys, appreciate that. And so I wanted to jump into this thing and see what we could find. One thing I kind of thought about after the video is what I'm trying to do is this amplifier board has a setup where you set 4.5 volts across this current source so you have the right amount of current. It sets up your bias for the Class A. And I set it up for 4.5 volts, but then I didn't notice that it dropped, and it didn't really register until after the test. So today we're going to look at that a little closer, and I think what I'm going to show you is that, you know, we talked about some grounding issues possibly and some other things, noise from the generator, which, yeah, the generator does put out a little bit of noise, but maybe not the signals we're looking at. We'll look at that. We're going to look at the TH2 with the Keithley meter, but I saw this interplay, and I saw a little bit of it in the last video, but I didn't really clue in to see how much it was affecting me. And when I was trying to set the optimization by adjusting this bias current, you know, for this range of voltage that you can get to set the amount of current, I didn't really see a benefit from that. And I think it was because as it was getting better, it was actually causing a bigger problem, you know, with this interplay. And has to do with the amount of signal we're putting out, the power supply. So my idea was to separate this from the AC to DC power supply, test them separately to begin with, make sure that I wasn't seeing problems caused by the two interacting. However, I think I saw an interaction between these two guys that I wasn't really thinking about. And now that I've seen it, it seems obvious, of course. It's like, oh yeah, should have known that. But anyway, it's been a while since I've tested a Class A amp, and it's been a long while actually. So this is a great thing to get back into. It was actually a good problem to run into to kind of, you know, see how these things work. So, alright, so let's jump over here and I'll give you a look and I'll show you. We'll look at the FFT on the mix sig, and we'll look at the current and the power supply, the voltage ripple on the power supply, and the interplay when we adjust the signal level, increase it, and we can see how by increasing the current here, which you would think would help, which it actually doesn't because of the lack of bulk capacitance that we will get in our real power supply, but we don't have here. Okay, so we're gonna have to wait to optimize it later is what it comes down to. But come over here and let's take a look and I'll show you. Alright guys, just a quick overview of the setup. I've got the board down here, and I've got the transistor sandwiched between this heatsink held by these clamps onto the heatsink down here, this big heatsink. And so they're sitting in a channel with some thermal paste, and then I've got this squished down. The last video kind of shows how I did that. And here's our power supply. Okay, the ground's coming into this ground connection I have. The generator is coming into the input terminal, which is right underneath, and its ground is also referenced there. So that is referenced to chassis ground at that point, earth ground, okay, and because of the generator. Then the black power lead goes to the black power input, and the red power lead goes to the red power input. And then this set of leads is coming around here over to that nice amp probe meter. I really like that amp probe, guys. That's a great meter. Anyway, we're going to look at the voltage there to set up our bias current down here, okay? I did that last video, but I'm going to kind of show how that, you know, what I'm seeing when I play around with that, okay? Okay, over here you see these differential probes coming in, and the minus goes to the return, the plus goes up to the output lead, and then we also have this lead right here, this orange one, and this blue one down here that's tied into here. Those leads here go over here to this load resistor. Okay, they're kind of clipped in right down here. That's an 8 ohm 200 watt load resistor. So that's kind of the setup right now. All right, so first we're going to look at the mix sig, and we're going to look at the current, okay? And then with the differential probe, it's going up to the GWN stack scope, and then we'll go up to look at that FFT. But the mix sig, I've got this current probe right here, and here's the differential probe that's going to the GWN stack. But this current probe is right here, and it's going to the mix sig. Okay, so we're going to focus on that screen and that multimeter. Alright, now what I'll do is I'll take my blast shield, set it over the board, keeps things from blowing up in front of me. Let me turn this around so it's not in the camera. There's a little bit of a glare in the camera, sorry about that. Maybe I can set my light differently, hold on. Alright, in the last video we had some extra distortion that we weren't expecting on the FFT. Well, let's just look at the current on that screen. Okay, right now it's 200 milliamps per division. We're right down here. Okay, let's go ahead and turn on the power supply. I'm getting the probe on the... Okay, and we set this meter about 4.5 volts. So let's go ahead and turn up the voltage here on the supply. Pops up, charging caps and doing all that stuff. Sitting here right about 1.36 amps. And we're right at 4.5 where we set it. Alright, so now let me bring up my input signal. I'm going to turn it on. It's being maxed out. And you can see it goes right off the screen, so I got to change my scale. So look at that current. It's pulsing current from the power supply. That's coming from this probe right here. And that's the plus power supply rail. And that is just not looking so great. So our current from our power supply is pulsing like that. The problem with that is we're 500 milliamps per division. 1, 2, 3, 4, 5, 6. That's 3 amps. This guy, my power supply is only good for about 3 amps, 3.5 amps maybe. And so right now I see a little red light glowing on the power supply. Hey, you see this little red light? So it's just trying to clip. So it's not providing enough current, so the voltage is drooping. So that's why we were getting that distortion. Now if I lower my signal for my generator, right there, it turns off. But now watch what happens when I adjust the bias current. So as soon as I start adjusting the bias current up a little bit, which helps take away the distortion, it comes back because of that. So that's why when I was adjusting the bias current and I wasn't seeing any benefit, is because I was fixing one thing and hurting another. Alright guys, what I want to show you is the voltage ripple. I took the differential probe, put it on the output, the mix-sig differential probe. So we're looking at the voltage ripple on the output, and see the ripple there? It doesn't look too awfully bad. Now that's just before my current limit light starts going on. Then when I turn up the signal a little bit, now the current limit light goes on in the power supply right there, but still that ripple doesn't look too bad, right? Alright guys, so I've got the probe AC coupled and it's 500 millivolts per division. So let's go to, whoops, wrong one. Let's do this guy, 250 millivolts per division. Okay, that looks sinusoidal, not bad ripple. But our signal is really low right now. Okay, now let me increase my generator signal. And you notice something that's starting to happen. See how there's a shift right here in the power supply? It's a sharp change, and it happens when this ripple comes up right here. So I'm still well below that little red light coming on the current limit. So let's, okay, right there it's starting to come on. And then you can see how bad the ripple gets on the power supply, and you can see how it starts affecting my signal too. But look at that. So you can, it's really pronounced right there. There's something happening every time a pulse occurs. So if I lower it down here, now it's pretty much just sinusoidal at that point. Okay guys, I got the FFT turned back on and I'm showing you those spikes right there. Now I've got the signal turned down low enough that it's not causing my red light on my power supply to turn on. So I've got it, so I feel comfortable that it's not the power supply causing that problem. I have to get enough cycles to get a good FFT. That's why we got so many cycles up here. But now what I do is, watch this. I'm adjusting the current on the output and see how that distortion is just dropping. So before I didn't see that because I had my signal too high and I think the power supply was creating up. Look at that, I can get it to drop right down. So we're supposed to have this about 4.5 volts and look at that, it's starting to drop right away. Now some of those high frequencies started happening when I got too high. You see that? Look at that. So now I have to go back the other way. So adjusting this, looking at the FFT is maybe a nice way to get your adjustments in. So we'll do this again as we get our real power supply running, but right there, that looks a lot better, right guys? Okay guys, I'm playing around. As I get about 4.5 volts here with the signal actually running through it, that's when that distortion looks like it gets pretty good. I mean, it drops down pretty low. And if I bring my input signal up, I start getting power supply distortion. I get that red clipping. So right there, I'm not getting clipping, but as I adjust my current, it'll create that clipping problem. So it's kind of a seesaw back and forth. So you really have to get the right power supply, the voltage rails that you want to run, and then adjust this compensation. But yeah, right there, it doesn't look too bad. Okay guys, what I did is I moved my differential probe over at the input connector. So the power amplifier's turned off. Here, I'll turn off. The power supply, power amplifier's turned off. I'm just running the generator in to the input signal, so it's loaded down by the circuit, and the differential probe's looking at it. The grounding's the same as it was in the previous test. The only difference is I moved the differential probe from output to input. And you can see the generator looks very clean. Now let me just move that signal out of the way. So this is the generator signal, this yellow one that I'm moving around. And there's FFT of that one. Here, I turn off the current since we're not needing that right now. And that looks very clean. That's 1.2 volts RMS out on my generator. I'll increase it to 1.3. You can see this signal increasing and the amplitude of this 1 kilohertz spike increasing. I have to probably move this down so it doesn't go off the screen. Okay, I'll go 1.7, 1.8, 2. Okay, that's 2.6. That's 3 volts. That's 3 volts out, but see how this signal's off the screen? So if I make this smaller, whoops. Put that 1 kilohertz spike right there. So yeah, I mean that's 3 volts out, which is way higher than we need for this thing. Yeah, it's 20 dBs per decade. And we're about, this signal up here said 7.4 dBs. So we're about 7.4 dBs above that signal right there at 1 kilohertz. And you can see these spikes, they're 20, 40, about 50 dB below. And that's at 3 volts RMS out on my generator. So I'm going to drop it down. 2.9. That's about 2.5. That's as high as we'll probably ever use for this audio stuff. And that's about 2 volts right there. So those spikes are pretty low, but you can see it's about 3K, 4. So that's coming from the generator. That might have been a little bit what we were seeing on the previous video, along with this topic we just covered. Alright guys, I got the differential probe back on the output, and I got the signal turned on, power supply running. You can see the signal we're putting in is about 900 millivolts RMS, and we've got some of those spikes from the generator, I think. And now if I increase that signal, see yellow signal increasing, and you see the distortion spikes starting to come up. We're 1.4 volts RMS, but the red light on the power supply is on. Right there we're at 1.3 and it is just barely off. If I drop it down, the harmonics don't look any better, so 1.3 I think we're safe. And then, you know, going back adjusting that signal again. Yeah, again, so I think when we get about 4.5 volts there is when we get about with this power supply rail and the combination of things going on, I think that's about the optimal level at this point. So when I turn off this channel, we have about 17.6 dB here, and these guys are 2040, about 44 dBs down. Whoops. Alright, so yeah, they're about, I'd say about 44 dB down maybe, and 17.6 dB. So we got about, we got right, I'd say we got a good 60 dB from signal to noise threshold. That's 60 dB, I think, is pretty darn good. Moving the differential probe back to the input, you can look at it's very clean, so that does appear to be noise generated from the amplifier right now. Now I've moved the differential probe over to the plus power supply rail, and I do see a little bit of a harmonic there at the 2 kilohertz. Okay, then when I bring my signal up, just monitoring the power supply rail there, that's 1.1. You can see those spikes starting to appear. That's 1.5 volts at my signal, and I do see that red light coming on the power supply. So if I drop it down, right there the light goes off, but I still see some spikes. And something else I notice is this 4.5 volts drops away as I bring my signal up, and the noise starts jumping up, the signal's dropping. So I think it's a play between the power supply not having enough bulk capacitance and being able to supply, a nice solid voltage, and we're seeing that. Now another thing is, let's say if I crank this up a little bit, we see these spikes coming through. Okay, we see some spikes, and then if I take I've got the scope being charged right now. If I remove the external power supply, I don't see any change at all. And what I have is a current probe and the differential probe plugged in. So at this point, what I have is power supply turned up 31.6 volts out. It's giving about 1.73 amps per side, and right here you can see we're set at 4.5 volts across that resistor. So I've compensated for 1.2 volts coming in. So I think what we want to do is, when we get our power supply and everything else set up, we want to set this bias when we have our max signal in to give our max signal out that we want. And then you can see how low the distortion looks at this point. So I think that is the optimal setup we want once we get our power supply arranged and our max signal. And that's with this power supply set up right now with our lab bench. I'm starting to see a little bit the red lights coming on. The distortion's starting to get to just below 40 dB, just peaking above this line a little bit, and we got about 19.17 dBs above the line. Now I've been running things for a while, so I did get temperatures up 59.6, so starting to get kind of toasty. You see about 54 degrees on the load resistor, so we're getting nice and toasty. The Keithley THD meter's showing about 0.04, 0.048% THD. Alright, so did that make sense? I think what we saw was the generator, looking at that by itself, it looks like it does create some noise, but when you get the signals up a little higher, probably higher than what we're going to be looking at. And then as far as grounding, when I remove the power, the external power source for the mixed sig, which isolates the scope, then the scope only gets its connection to ground from whatever the probes are connected to, and we only have a differential probe and a current probe. So by disconnecting that external power, didn't see anything change there. So the circuit is grounded through chassis, through the generator, because that's tied to chassis. And you know, and just in regards to chassis, anything metal, agencies will say you have to have that tied to chassis ground, so everything is referenced at the same level. So I don't touch a floating scope and then touch my power supply and go so they say, you know, don't let some human equalize the voltage potential. Make sure they're all tied to the same chassis ground. But if you're using a floating scope, like a battery operated scope like that tech up there, or this one down here, now that tech up there actually has galvanic isolation between channel 1 and channel 2, and you know, those two channels are galvanically isolated from input. So input power, channel 1, channel 2, they're all isolated from each other galvanically, and that's great for a lot of things. This mixed sig is almost like that, as long as you pull off the external power supply. Then, but still, you have 4 channels on this mixed sig. All 4 channels, the grounds, the BNCs are tied together, right? So the metal, you can actually touch them, so that could be dangerous if that was floating. If I'm looking at, say, a tube amplifier at 300 volts, or you know, some high voltage, and I'm floating my scope for that reason, you know, some people do that. Hey, people float scopes, and if you're doing that kind of stuff, you got to be very aware of that, because those BNCs will be floating at whatever potential they're tied to. And if you're touching a BNC, or you know, what you think is a low voltage ground, well, it might be low voltage compared to something else, but when you touch your chassis, you know, it could be, anyway, safety issue. Sorry guys, went off on a tangent there, but anyway, so manufacturers will tell you to chassis tie everything so it's safe. Now, we didn't see any problems like that. We didn't see a lot of distortion from the generator, especially at the levels we're using. But what happens is when you're setting this current here, and you set it for a higher current hoping to lower the distortion, the problem is this power supply is seeing those peak currents. It's not seeing the average 1.5 amps or 1.6 amps. It's seeing 3.5 amps, or you know, 4 amps. It's seeing higher than what it is supposed to put out. Just doesn't have the bulk capacitance. So once we get our AC supply hooked up, you know, I could put a bunch of bulk capacitance on the DC supply and improve it, but next video, guys, I'm going to show you another power supply design. It's much like this. It's just another kit I bought. We're going to put that together, and since this one's all put together with all the capacitors, that one I'll put one cap on the bank at a time and then add them, and we'll see how it improves it, okay? But once we get a beefy, stiff, you know, plus or minus power supply on this thing, then we can optimize that bias current, and we should be all good to go. Because we did see the Keithley, when we optimized it at whatever levels we were set to, it did put out, what, 0.04% THD. So that's pretty good, I think. What do you guys think for the Class A? I guess we could do some research, see what other people have got in these Aleph 5 Class A's, but I think anything less than 0.1 sounds pretty good. So, alright guys, leave me your comments, and thanks patrons for all your support. Thanks everybody for watching the videos and supporting the channel, and all your great comments. Really like doing that, trying to answer them all. Sometimes some of them get buried, especially when it's in a comment, you know, the 3rd or 4th comment. I don't get notifications, so I have to go dig deep for those sometimes. So but I do try to answer them all. And thanks, appreciate it, and we'll see you next time.